Welcome to a quick lesson on a handy way to use equations. Even when we don't have givens, we can still use it to make predictions about how variables relate to each other. Uh, these are meant to be notes in one of the extra notes pages at the beginning of a workbook unit. So every workbook unit has a couple blank pages at the beginning that are for things like that. So find some space where you can record some of these tips, and we'll show you an example problem. And I think it's something that you'll find to be pretty handy. So this fill in the blank predictions. So it's a way that we can use equations and use the principles that we have without knowing givens. So we can when we can talk about if we double or triple one variable, how does it affect another one? So it's taking again our relationships between variables and going a little deeper. So if we're going to do this, we have to obviously, identify ID the variables involved, like, think about what the variables that we're going to use are, and, find an equation that links them. Find a single equation. It would be a way to put that, not equations. Now, when we have that equation, we're going to write it um, with blanks in front of the variables. And it's going to be the things that we put in those blanks, these multipliers, that will tell us um, how changes in one variable can affect another. So we'll write that equation with blanks in front of the variables. Couple things. It would be smart to rearrange the equation to get the variable in your claim, the one you're making a claim about, get that one alone. So if I want to say that speed will double or triple, or that distance, or any other variable, the variable I'm making a claim about, get that one alone in the equation. The other thing to know about then is only the multipliers. And what is a multiplier? That's going to be the numbers that we put in the blanks. Only these guys will matter, will count for calculating a change. Or for what I should say is predicting what's going to happen. So check out this example, and I think it'll help. So for example, if we're trying to study which variable has a bigger effect on a car's stopping distance, if we want to decrease the stopping distance, we're looking at safety in a neighborhood or something like that. Well, should we try and get better brakes, or should we just try to get drivers to go at a lower driving speed? Which one of those would have a bigger effect? So what are the variables in the relevant physics equation to consider? Well, clearly I'm talking about v initial here, or v original, that's driving speed. I'm talking about acceleration. I'm talking about the stopping distance. And there's one other one here that's worth bringing up, because we know that v final in this has to be 0. And when I bring that into the picture, that really does make it easy to find an equation that links these, because v final squared equals v original squared plus 2ad. And we said, hey, the thing we're making a claim about is about effects on stopping distance, right? So I'm going to get that alone. If the v final is 0 and I solve to get the stopping distance alone, well, this equation rearranged is going to be v original squared over 2a. Okay, now, so we have the equation. How is this equation going to be useful to me if I don't have any givens? Well, just look at this question down here. If we were to get twice, if we doubled this acceleration, how would that change the stopping distance? So I'm going to write my equation with blanks and only numbers that would go in these blanks are going to matter. This 2 won't matter because when I go to change one of the variables, when I change the deceleration rate, that 2 was there before we made the change and it's there after. So it won't contribute to causing a change in our stopping distance. We want to find out about what's the change in the stopping distance. So we're saying we have twice the rate of deceleration. Now we can already see that stopping distance and our acceleration rate, one's on top, one's on bottom, and so that already indicates an inverse relationship. A greater rate of acceleration means it's going to be a shorter stopping distance. So we can already see that, but we can get more exact about how exactly it works. For any variable that we're not changing, I put in a 1. It means that variable hasn't changed. So in this case, we didn't change the driving speed. So we're saying if you're at the same driving speed, we improve our brakes so that you get twice the stopping deceleration. And what happens here then is if I look at my numbers, I have 1 squared, because whatever we're doing to the variable, we do to the multiplier. 1 squared divided by 2, which, if I put that into a calculator, comes out to be 0.5, 1/2. So it's saying 1/2, 0.5 of our dx. In other words, our distance is cut in half. If we can improve our stopping deceleration, if we can double that, then it'll take half the distance to stop. Oh, okay. Well, that's pretty good. What about if we were to change the velocity? If we cut that driving speed in half, how would that affect it? So we'll do the same setup again. We'll take the equation, and again, notice how the only thing I'm really paying attention to is what goes in the blanks and what the equation tells me to do with those, and I'm just working out the proportions. And when I do this, when I fill in the blanks, that's going to tell me what the ratio, what the change is that goes in front of the distance, because any change we make over here on the right side has to be matched on the left side. So now we're saying let's have the same acceleration, but we go with half of our driving speed, half of our initial speed. Now, there was a direct relationship between distance and speed. It makes sense that if we're going slower, it won't take as much distance to stop. But is it just cut the speed in half, cut the distance in half? Well, the equation is pointing us to something a little more involved, because it's 0.5 squared over 1. And if I type in 0.5 squared in my calculator, it'll be 0.25 of the dx. So in other words, our distance required for this is 1/4 of what it has been. We can see that changing the velocity has a bigger effect. Now that isn't surprising since velocity is squared in this equation, but we can see exactly what it is. And where this can really shine is when we start changing more than one variable at a time. So what happens if we were to change both of these variables? Then what would the effect be? Well, I'm going to take the same equation we've had, and I'm going to fill in both those blanks. And so, what's the change in the distance if I both cut the initial speed in half and I double my stopping distance? Well, when I take 0.5 squared divided by 2 in my calculator, that gets 0.125, 12.5% of the dx, or 1/8 of the original distance. So if we were to make both of these changes, we would see a huge reduction in the stopping distance. Okay, so this is an easy way for us to be able to quickly say, if I change one variable or even multiple variables, what happens to this other variable. We can use our equations to make these predictions, and very nicely, when we do this and we show this, we're also providing pretty solid reasoning to back up our claims. So uh, I hope you find this handy, and I think you'll find some opportunities to use it in a variety of situations. Thank you for watching.